Hello and welcome back to Old School Coding. So, next thing, you can see off on the right, I have a data sheet for a Schottky bipolar 8224 clock generator and driver for the 8080A CPU. Okay, so the 8080 has a bunch of funky logic in it that requires a two-phase clock. And to generate this, you do all sorts of interesting things inside the 8224. And we are going to be modeling some of them. So on the diagram here, we can see that it's got an oscillator that turns out a oscillating signal at some frequency, which nominally is going to be 18 megahertz, but I don't think the 8224 will talk about that too much. That goes into a clock generator chip, and it may or may not show up on the video here, but this is labeled clock gen divide by 9. So we're going to take this 18 megahertz signal, and our outputs are going to cycle with a period of 2 megahertz, which is precisely correct for what I want to do. It has some clock drivers for the oscillator, phi 1 and phi 2. So those are intended for large fanouts. It's got a phi 2 TTL, which is going out TTL levels. I'm not sure why they're separated. I've looked at schematics of 8080 based systems, and there's a little distinction there. I probably missed something. Then the lower half of it is more than just the clock generator. What we're doing is we're taking some selected outputs from the clock generator, and we're using them to do two things. First of all, if there's a sync signal coming from the CPU, this is a signal that the 8080 turns on during the first T-state of an instruction, actually T-state of a machine cycle, I think. It will take that sync signal and some intermediate data from the clock generator and use it to generate a status strobe value. This is a value that will go low briefly, and it will clock latches that will take from the 8080's data pins a set of 8 status values that typically could change each machine cycle, though more often. So that saved the 8080 a bunch of pins. Internal complexity to get those on the bus at the right time, but reduction so that it fits on a 40-pin dip. It also, the 8224 also says, well, if reset is active, I'm going to hold the STSTB low, because apparently in the following chips, there's an idea that status strobe being low for a very, very long time means we're in a reset cycle. That's okay. We will think about modeling that. I will think about whether I want to model that or not. The other thing it does is at some other point, let's say that was marked as phi 1A, phi sub 2D clocks these two flip-flops. And one of them takes a reset in, which is active low, runs that through a Schmidt trigger, and sends its inverse out on a reset signal, which is active high. The idea there is when you power up the system, reset in starts at 0 and then gradually comes up to a 1 level because it's basically on an RC circuit. So it takes some time to go up, and the Schmidt trigger assures that as it ascends through a given voltage, the output of the Schmidt trigger goes from 0 to 1. And if it wobbles a bit, it would have to come down below a certain level to go back down to 0. This also means we can put a thumb switch on resin, and if you hit the switch, it will drag resin to 0, and the Schmidt trigger will trigger, and that will put reset. So active low to reset, and the output of it is a signal that is high when we want to reset the system. Okay? So reset resin will be sampled at some point during this half microsecond period. Ready in also, there's a ready signal, which is active high for I'm ready, and that's also sampled at that same edge, and it produces a ready. So ready Y in is asynchronously set by somebody, and at some point during this this T-state, this time of half a microsecond is called a T-state in the rest of the system. So some specific point during the T-state, we sample that and we hold it until the next T-state. So reset and ready are preconditioned synchronized signals produced by the 8224. The idea was that this took the place of a whole bunch of discrete logic. Now I am going to scroll this. This is actually the entire MCS manual. I'm going to scroll backwards through this whole thing. So if we go back to where it's discussing the 8080, back here, we're discussing the requirements of the 8080. This is actually the picture I've got for my thumbnail for the series. It shows a whole bunch of things, and here's your basic instruction cycle. And we might as well look at this in context. Our job is to create phi 1, which is this top thing, which generally is low and blips high at the beginning of each t state. And phi 2 goes high after phi 1 comes down, and it's high for a while, and it comes back down before the end. So phi 2 is high during kind of the middle of the t state. And there are things that happen. And we'll notice that ready is sampled by the processor when phi 1 is high. So we need to do that triggering sometime before phi 1 goes high. We'll be more specific later. Status in, oh, wait a minute, that vertical line isn't, that vertical line doesn't touch ready. So this diagram tells us that the person that drew the diagram believed ready changed there at the beginning of the t state. However, this line right here, my mouse cursor is showing up, indicates that yes, indeed, the ready line is being sampled while phi 2 is high. And at some point while it is high, it's going to notice it, and we're going to say, oh, we're not ready. Ready is low. So we're going to insert a wait cycle. And at some point here, between this falling edge here and where we notice it over here, sometime between this range, I need to sample ready again. I need to latch ready in the 8224. Now, what I was actually going for was not that diagram, although that was interesting and informative and will be things that we bear in mind. There is a discrete logic diagram here. So if you're not using 8224, this provides a clock generator. Now, it is slightly different. If you actually implement this clock with this external discrete logic, the timing of phi 1 and phi 2 out of this circuit is not the same as the timing out of the 8224. The timing diagrams look different. And we can see here on these waveforms, this is what this diagram does. And it actually talks about phi 1a, which is a gating signal. Can I point at it with my fingers? Yes, it's here. So phi 1a is oscillator will clock us on a rising edge, and we're looking at this signal. So this QD, this output D from this counter, which starts at 3 and counts up to 9, counts up to 3 plus 9 is 12. When it gets to 12, it loads a 3 in, blah, blah, blah. Anyway, I implemented this logic discretely in a little simulation and checked it out. This has been months ago. And then I checked out the timing diagrams, the 8224, and they're not the same. And I decided that I wanted to go with the 8224. The other thing that I wanted to look at, I wanted to point out here is this shows this oscillator running at 20 megahertz. The MSI 8080 runs at 18, and a lot of other timing diagrams I see kind of assume half microsecond time. So this 20 megahertz is actually too fast for the 8080 that I was looking at. But having it 20 megahertz makes it really easy for them to talk about what this circuit does. Also notice that it samples and holds ready and hold rather than reset and ready. So we're not even dealing with the same signals here. So rather than simulate that discrete logic, which is actually fairly clean, I went ahead to the 8224. We're going to do an 8224. So what does that involve? Well, 8224 does not disclose the contents of this clock generator. But what we have is a system that steps through 18 states. as the oscillator goes up and down. So we've got high 1 and low 1, and high 2 and low 2, and high 3 and low 3. But we only really need to look at what's happening on rising edges, because the oscillator rising edge is what changes the clock gen, and it doesn't come anywhere else. So nothing happens anywhere but on rising edges of the oscillator in this chip. So we really have 9 states. And if we look at this timing diagram down the lower right, we see indeed this says that we are dividing the primary clock by 9, and during states 1 and 2 of it, for 2 states, we have phi 1 high. We have 5 states with phi 2 high, and then 2 more states with both of them low. So that's the first thing we will simulate. Let that sink in for a moment. Now the next part of it is this latch. When are we latching this? We're latching on something called phi 2D. They do not describe phi 2D specifically, but they do include it in a timing diagram. So here we're talking about how it gets hooked up, and the fact that the status strobe goes to the 8228, which we will talk about after the 8224. And when we start looking at timings, we see the timing diagram here. And what I'd like to do is have some kind of output from the simulation eventually, maybe not today, which will actually show us something graphically that'll do this. Maybe in bad ASCII graphics, because I'm not going to hook up a big X window thing. But I can draw with underbars and dashes and up arrows and slashes and backslashes. So this shows us that we have a rising edge and a falling edge, and we have a very specific set of timing requirements. So phi 1 pulse width. Now this is for a cycle time of 488.28 nanoseconds. So we would need to recompute this for our cycle time. Grumble, grumble. Does it give, oh, okay, so here we actually have a table that gives it in terms of TCY. So what I will do is I will write a little bit of Python code to take in TCY and produce us these numbers. But let's go back to looking at this. If we talk about TCY being 500 nanoseconds, which is our target, that's only a little bit bigger. So for 500 nanosecond total TCY from rising edge of phi 1 to rising edge of phi 1, that's going to be about 100. So, yeah. Actually, it's about 90. But we do know that this is 2 cycles long. So for us, if TCY is 500, we're divided by 9. So it's 55.5 times 2. So we know that for us, this pulse width is 111 nanoseconds wide. So that's greater than 89. And I'm going to make this bigger. Since we're mainly focused on this diagram right now, I think I have 2 pages here. Yes, those 2 pages come up side by side. That is good. So, TCY. Phi 1 pulse width is at least 2/9 of the whole thing, so 2 oscillator cycles, not more than 20 nanoseconds short. So we can have 20 nanoseconds short of that. So we'll make that exactly 2 CY over 9. And phi 2 is 5 CY over 9. That's what we were looking at here, though, 2 cycles of this and 5 cycles of that. The delay between them is at least 0. That's basically saying that phi 1 and phi 2 should not overlap. And the 8080 actually demands this. If we have phi 1 high and phi 2 high at the same time, we're in trouble. One could say that you would want an extra cycle between them. And the discrete logic we saw before had phi 1 high for 2, and then both low for 1. And then phi 2 is high for 4 cycles. Okay, so it delays phi 2 by 1 cycle. So what happened was the 8224 pulled this in and said, instead of having a oscillator cycle of dead time here. We'll pull this rising edge in to be on top of this falling edge. So it's falling and rising. This is actually from the time it hits low to the time this breaks away from low is at least 0. Our rise and fall times are precisely 0. So all I have to do is assure that I handle all of the services for the descending edge here before I handle any of the services for the ascending edge there. We will stay predictable. Okay. So phi 2 to phi 1 delay, this is TD2. That's from falling edge of phi 2 to rising edge, is at least 2CY, or 2 ninths of TCY minus 14. So this is 2 cycles, might be 14 nanoseconds shorter than 2 cycles. So these little, 14 nanoseconds or so on, this takes into account the fact that in real electronics, it takes time for a signal to go from high to low. Then TD3 is from rising edge of phi 1 to rising edge of phi 2. We are limited. We have somewhere between 2 CY over 9 and 2 TCY over 9 plus 20. So this says that we are guaranteeing that from here to here is 2 ninths, not 3 ninths, not 2.5 ninths, 2 ninths. So that forces our timing of T1 and T2. We already knew that. See, phi 2 TTL has the same timing as phi 2. There are some allowable slop in here, 5 nanoseconds earlier or 15 nanoseconds later. We're not going to worry about that. We have a sync coming in from the 8080. I notice there's no timer requirements on that, but there will be, the idea is that this sync needs to be high while status strobe is low, because somebody else is going to be looking at status strobe and sampling the sync data. The CPU places data on the data bus when sync is high. We want them to sample it. We're good. So this is the next time we're going to look at TPW. Status strobe pulse width is no less than 1/9. So this is 1 cycle, as much as 15 nanoseconds less than 1 cycle. So this is 1 cycle wide. And the way it's drawn right here is its rising edge looks like it's about the same time as the rising edge of phi 1. So this will be in the 9th part of the V phase, not the 8th. Makes sense. We've got a little gap time there. So we're pushing this to the very end of the T state. Okay, now notice that it has ready or res in, so we have the signals that we are sampling. Remember, the thing that we couldn't determine was at what point are we latching ready and reset. Well, here's where we're doing it, right here. This is TDR before the falling edge of phi 2. TDR is at least 4 cycles before. Well, this is 5 cycles long, and we're at least 4 cycles before it. This means that this point is, of the 5 cycles, it's 1 cycle in. So how does that match up with everything else? Are there other requirements on this? So this is just saying that we are TDR. Let me check that again. So there's no maximum. So as far as everything is concerned, we could latch sooner. We could latch on the rising edge of phi 2 if we wanted. Okay? But I think what I'm going to do is go ahead and latch this. So if this is cycle 1, cycle 2, cycle 3, we'll latch this at the rising edge on cycle 4. And that gets ready in and ready out. Our inputs, there is a hold time requirement, and the hold time is measured from the leading edge of status strobe. That is weird. That is really weird. Oh, right, because whoever is going to assert those signals will be responding to something. So TDRS is, we need to have these stable before status strobe by TDRS. TDRS is 50 nanoseconds minus 4 ninths. What? That's a big negative number. So setup time is negative. Yes, negative 167. So it looks like TDRS, which is drawn here as a very tiny positive value, is actually a big negative value. It's like 3 cycles afterwards. So this is saying that from here to this edge could be way out here. So, yeah. So we're sampling this. So we're going to set this edge high in one oscillation, and the next oscillation will do this. And that, I think, covers all of the things we want to do here. So we've got our two-phase clock, and we're settling in on, internally, we're going to be stepping through 9 states. And at each rising edge of the oscillator, we're going to do something. We're going to have a rising edge of phi 1, or a falling edge, or a rising edge, or here between 1 and 2, this is where we're going to do the sampling on these D latches. And the status strobe is going to be out here in this second dead time here. So I think we have enough information now to start actually writing some software. So let me put this back to one page, and I'm going to move it out of the way a bit. First of all, if I turn that back on, I want it to come up on that right-hand side there. And now I'm going to remove it from OBS. If I don't explicitly do that, I forget. And over on my screen, I'm going to do some stuff off screen to start my build system running. And we're just going to let that churn. And okay, so I've got the data sheet. It's not on the part of the screen that I'm recording, but I can still see it. So let us start building this thing. Compilation window in the upper left. Okay. I have been messing around a bit. I have some things in a Windows D drive that are for the recordings. I was getting stuff set up there. Let me just kind of remove everything from my Emacs. I should probably set up an Emacs macro that resets my screen to this layout. So here we are. We're ready to start building the simulation of the 8224. So we need a header, 8224.h. And we need a source file, 8224.c. And we are going to need main.c because it's going to start doing things. Now, because I am on Linux and I have stretched my editor all the way up to the top of the screen, the fact that my webcam takes up about 2 millimeters of the top of the display means I can't actually see what's going on right here. So I have to look around. Yeah, okay, so I'm including 8224.h in my source file. So let's start off with the usual thing we do for all of our modules, which is the post, BIST, and so on boilerplate. I'm going to use this window up here temporarily to bring that in from, let's pick one at random. How about clock? So clock.h, we have post, BIST, and bench. Now, I can't call something 8224 underscore this, that, or the other, so I'm going to have to replace clock with I8224. Now, if I'm going to do that, let's actually call this I8224. Needing I for Intel, it's like you have I8080 and so on. That means I need to go up here, and this needs to include I8224.h. And now I need to set up my functions here. Okay. Declarations, functions, they're doing nothing, but they're printing stuff. I've got my build going over there. I can now go in here, and wherever I have clock, I'm going to add I8224 after that. Okay, that built. And I, of course, have a typo, 8224.h, no such file or directory. And that's up in here behind the webcam. That's better. So now when I do my quick build, what are the differences I see? I see we have a top and end for post. So you have a top and end for BIST. We have our benchmarks, and we have a top and end for the bench. So I can remove those print statements because I know that those methods are being called at the right time. This should have a very strong sense of deja vu, which makes sense because we're following a procedure that has been evolved to do the right thing for this system. So I have my power on self-test ready to go. I just need to hook it up and have it work. So what is an 8224? We're going to look over at the diagram here, and then I'm going to look back and start defining this thing. So type def struct I8224 underscore s. Is that the convention I'm using? Let's make sure. I'm using s. And it's a star P8224. Actually, I'll do that. So I'm going to deviate from the convention. Previously, I had a lot of types whose names were all text, and they started with capital letters and so on. For chips, I'm just going to use a lowercase I. So it's I8224 is the name of the type that is the array of one of these things. And instead of I, I'll use S and P for the structure tags and the pointers. And I am declaring that to be a new convention to use when I'm modeling a chip from Intel. Now, what has it got at the top? I am going to need well, let's flash the PDF back up. Now you can see that I need, I'm not going to model the oscillator. We are doing a digital simulation. The oscillator is inherently analog. I don't want to do RC simulations of the crystal. So what I'll do instead is oscillator will be an input signal rather than a created signal. The oscillator itself is clock. Okay. We'll also need, so oscillator's input, phi 1 and phi 2 are output. Status strobe is output, reset is output, ready is output, ready in is input, res in is input, and sync is input. So I need all of those things. Those are all edges. I'm going to leave this up because I'm going to be messing around in the header file only for the moment. So let's start off with p-edge oscillator and p-edge. Do our input signals first. So oscillator is a primary input signal. We have things that we are sampling. We have p-sync, p-edge sync. These are going to be very similar. Sync and res in. I'm putting an underbar after it to say it's active low. That matches the bar over the name. Kind of a convention that might turn into being useful. And ready in. Notice res in is active low, ready in is active high. Oscillator, sync, res in, ready in. Are there any other inputs? I think that's all of our inputs. So now we need to declare some edges. Outputs are phi1, phi2. I am not going to produce a separate signal called phi2 TTL. I am going to produce an STSTB underscore and a reset and a ready. So there's our external connections to the world. Now internally, I need a state. So I'm going to say int state. So as I am called up by the clock, oscillator runs, at each rising edge of the oscillator, a function is going to get called. It needs to know which of my 9 states it's in. So we have state. And that state reflects whatever's going on inside the clock generator, which is a divide by 9. Lord only knows what values it's taking on, how it's reset. It's probably not anything like the thing we were looking at. I'm suspecting that it's a lot more complicated logic than that, because phi 1a needs to be high for only that one cycle. So maybe it starts at 0 and it has the value 8. So phi 1a would be the most significant bit, and that goes back to 0. Maybe so. That might be an interesting hypothesis. Not really important because we already know the timing that we want. Okay. So I am going to put that out there. And I compile it, and I don't have a definition of p edge because the header file doesn't know itself from anybody. So we're going to pound include edge.h, because if you are doing a chip, you need to know what edges are. And that now runs, well, it compiles and does nothing. There's also some things we want to have available to us. Let's go back to looking at subs.h. I know I need an invar and an init. So verify the invariance for the. And we're never going to capitalize the I in I8224. Intel never did, so I won't now. So verify the invariance. What are our invariants? None of the p edge fields are null. We need to have all of our provided edges hooked up to something. So somebody else owns the oscillator. We're just sampling it. A lot of people are going to be sampling it. So if I owned it, somebody would have to set my clock and his clock and his clock and his clock and his clock. By having everybody read from the same clock, we now have all of the subscribers in one list. Boom, we're done. So we don't own oscillator or sync or reset in or ready in. We do own these 5 signals because we are the unique person that sets them. So if you're the only person that sets a signal, or if you're the only person that receives a signal, then you can own it. If more than one person, if you are a observer and there are other observers, or if you are sending out data on a signal and other people are too, then you can't own that signal. Somebody else has to own it. So there's our invariant. All of them are null. State is in a valid range. There may be other invariants that come up. I don't know. I may not have to add anything else to that structure, to an initial state. So our initial state, we have actually something more we need to do. When you start doing these chips, we've got these links we have to set up. What I'd like to do is have an init function you call that doesn't assume your pointers are set up. It initializes everything you own, and then a second thing you call when all of your pointers. So if I have 3 chips and they're all exchanging edges, we call each chip and say initialize what you own, and then we set up all the pointers, and then we say, okay, now you can finish your initialization using the pointers that we've established for you. So we know that this pointer, my oscillator, is actually pointing at a real edge which has been initialized. So we now have 2-phase initialization. I'm calling the second one linked. because it says we're linked into the system. And we had some parameters there of the wrong type. There we go. So I'm not sure why my live coding thing is not often going for the right thing. Sometimes when I update a header file, my little script isn't going. I have probably blown my iNotify setup. Okay, let's look at the C files. Apparently it's not looking at the headers, so i8224.h is not seen by my little script. That's done in the wait target, iNotify wait, H source, C source, yada, yada, yada. I am going to, well, what happens if I say make Q equals, and I'm going to put a wait at the beginning of this. So this says, okay, it is listing I8224 on that list. So if I modify I8224, those weights should come up, and they did, they triggered. So I don't know why it wasn't triggering before. Anyway, so we're back up and running. Fine. So we have this linked thing we're going to do now, and that is, if you have multiple chips, you initialize all the chips, and then you set the p edges to non-zero values, and then you run the linked, which says, okay, now you can do stuff based on knowing these pointers are pointing at edges that are all set to their initial values. And now I'm going to switch over to the C file. We still have the data sheet sitting there in front of the right-hand panel, so I'm going to work in the middle panel on this. And what am I going to call this? I can't call it I. I is used to, I would call this gen. There. So now we have these functions, and they take a gen as input. This is a clock generator, and we are looking pretty good here. And sometimes my script runs, and sometimes it doesn't. I don't know what's going on with iNotify wait on this thing. Okay, that's going to bug me, so I'm going to remove this $C. So now I will be able to glance down at my lower right to the terminal that's running the builds, and I will be able to see precisely what is going on. Okay, implementation. So I'm going to grab all of the fields here, and I'm going to make some comments because I'm going to be touching all of those fields, or most of those fields, in several of these things. So invar will check invariance, init will ask for initialize, and linked is the post-initialization stuff. So invar. Assert that I've got one, because you might call invar on a p edge which is not set, and this assures you have one. So the true invariants are going to include these guys being non-zero, so we can't call invar until we get into linked, literally. This, again, is something where I might need an internal invariant and external invariant, where the internal invariants allow these to be null until something is set to you're done. So what we're going to do is we're going to say assert, we're going to say edge in var on all of these. Okay, I've got a cat that needs talking to. Hey, Lucy. You saying hi or you want to be picked up? You just wanted to say hi. Okay. She didn't really want to be picked up. She just wanted to have people acknowledge her existence. So, one of the nice things about storing an array of one something is because it looks the same whether you're dealing with a pointer to an edge or an actual edge. Now, I'm going to run state from 1 to 9. So a 0 state means you're looking at a structure that was filled with zeros and hasn't really been set up. Now, it could be in the future what I'll do is I'll use state 0 to indicate, yeah, in fact, that's an idea. State 0 says none of this stuff is set yet. Ha ha. Okay, so state 0 is a valid state of the system. And if state is greater than 0, then we demand that our imported edges are valid. Now, I can't just say state, I need to put gen arrow in front of all of this crap. Or do I? Let's see here. Int state equals gen arrow state. That's clean. And now the rest of this stuff, I only mentioned these names once, so there's no need to cache them. There is our invariant check. So state 0, haven't set things up. But once we get into linked, state has to be 1 through whatever. So if state is equal to 0, I'm going to assert that these are all null. Okay, so either it's state 0 and null pointers or not state 0 and valid edges. Okay, I may add invariants later, like saying phi1 and phi2 can't both be high. I may add an invariant that says if reset is high, then STSTB has to be low, and so on. I may also add an invariant that says if reset is high, then ready has to be low. Because the normal startup for this is you hold reset and not ready. You bring reset up and then you release ready. So front panel startup uses 2 switches in that order. So you're actually holding it you're holding the reset, but you're holding the CPU in wait states after it comes out of reset briefly. And I forget why you had to do it that way. I just remember you had to do it that way. Okay, so there's our invariants. So initialization, I'm going to assert gen right at the top here. Now, normally I would just go ahead and use it and we would get a segmentation violation and yada, and I go, oh no. But in this case, I do want to do an assert so that we very quickly get back to source code, because when we get a signal that kills us, we're not getting a traceback in that compiler window. We're not getting a listing of, oh, here's where you were when that segmentation violation happened. Maybe someday I'll put that code in. It can be done. It can be done in 1990 techniques, but it's a bitch. Getting source file names and source line numbers is just, it's all compiler specific crapola. Okay, so initialization. we're being called with these p edges probably still null, so we're going to ignore them. However, each one of these edges we want to initialize, and then if they need to start out high, we're going to set them that way. And I'm going to put in the line, okay, so my macro is not good. Undo back to, oh, right, I forgot to remove the line that had that. Okay, so let's try this again. Find the semicolon. I'm going to delete from there to the end of the line, delete from that to the beginning of the line. Now we go boom, edge, init, gen, arrow, name. No. Now this is the kind of stuff I was doing back when I was interviewing Rob for his job at NetBoost in 19 mumble. Something's just, yeah, this is typical of the workflow. Find the semicolon, delete the end of line, go back to here, delete the end of line, go back to here, boom, boom. So there's phi 1. Capture that, edge, init, gen, arrow, foo. Edge, high, gen, arrow, foo. Okay. So phi 1, we want to leave it low. Phi 2 gets left low. Status strobe, we are going to leave low because we're going to force status strobe low when reset is high. In fact, I'm going to assert when we get linked up that when we start the simulation, the res-in value here must start low when we boot the simulation. So we're going to start with status strobe forced low. Knit reset. Reset's going to start high. Ready is going to start low. Now, just in case we reinitialize, just realized, I should explicitly set the values of these signals, high or low, no matter what we do, just in case edge init isn't. So that's low. That's low. Status strobe is low because we're in reset. Reset is going to be high, and ready is going to be low. And I want to have gen arrow state initialized to 1. Do I? No, not yet. It's 0 because we haven't done the linked step yet. Linked. So linked comes in, and we are being told that all of these guys are valid. So what I'm going to do is I'm going to do I8224 invar gen. Oh, do it there too. So when we return from init, we're invariant with state set to 0. I am being told now that these guys have been linked up and they're in the valid steady starting state. So I'm going to set state equals to some, I'm going to set it to 9. So the first time we call, we're going to increment, wrap, and go. So state will be the, no, state's going to be the number of the next state we execute. Yeah. We'll see how that works later. So obviously state is 1, and we're going to run the invariants. And the invariants are going to check all these, so they will do the edge invariant check on our imported edges and make sure that everything is still cool. And I'm going to further add some more assertions here. How do I get the value of an edge? Did I set up an edge get? I don't think I set up an edge get, so I have to say edge arrow value. So what do I want to assert on power up about each one of these signals? Well, a gen arrow os arrow value. I'm going to start out demanding that when we power up, when we start things going, that the oscillator starts at 0. I'm going to demand that the sync starts at 0. Let's set up tests for all of these. Reset input is going to be 0, and ready input is going to be 0. So we are a valid ready, we are not a valid reset, reset asserted, ready not asserted, sync is low, and oscillator is low. And at this point, if there was any other computations we needed to do during our initialization based on the values of the input signals, we would do it. But instead of computing what is going on, so for instance, I would maybe take sync and do all sorts of things to compute the output values. No, I am simply saying we are initialized into the appropriate initialization set for our output, and we are demanding that our inputs are in the initial state for input. And that does compile and build. I'm wondering if I'm in the right directory. CD. Well, it was actually using the modified iNotify wait. Yeah, when I update i8224.c, that iNotify wait is not terminating. That's interesting. Because I'm running the same distribution of Unix, of Linux, right now, standalone, that I'm running inside WSL. So I may not have configured it properly. I may not have expanded the iNotify wait stuff. There's probably all sorts of log messages coming out at this point. So what I'm going to do is I'm going to shut down a little thing that says automatically run this when I save, and I will just run it here like that. So we may run this a couple of times to get the thing going, but that means that we won't be compiling every time I save. That's fine. So this should have us properly set up. Now, for power on self-test, what I want to do is exercise some of this stuff. So we are going to do i8224 gen. We're going to init, and then we're going to invar, and then we're going to linked, and then we're going to invar, and this should fail because I'm not setting it. So there we are. We have an assertion that gen sync is failing. So what is happening here is that because I am not hooking up any signals before I call linked, it is just having a field day. So let's turn off the data sheet. So for my test, I'm going to need to actually generate those signals. And what I want is the oscillator to be low, sync to be low, resin to be low, and ready-in to be low. Is that what I am checking the invariance? Yep. Oh, reset is high. Right. Reset is high because resin is low. So now, take those same 4 names again. In fact, why don't we not declare them until we need them? And once again, Greg doesn't look at his macro before he starts executing it. Okay, you run this enough times, it becomes idempotent. So assert gen sync is null. Now this isn't giving me a traceback at this point. So what are we doing here? Probably because init isn't clearing it, so yeah, I am asserting that it is null when that's a bad thing to do. It may not be null. In fact, those pointer values are indeterminate when state is 0. That's better. So we declare the generator, and then we hook up each one of its signals. And we say it's linked, and we do the invariant. Now, we haven't done anything else. I am going to make a little static I8224. Actually, we're going to do a P8224, I8224 new. And we're just going to take all of this. Oh, we need those symbols. So how about we do this? I'm going to make these. So we're going to do a bunch of static things. For testing. And this is going to be test I8224 test init. That was good enough for, so the only difference is for bench, I will need to do this without, well, no, I can use it. I can use it for that. So post and bist both need the invariant checks, and bench doesn't suffer from them. And this is going to return void. So test init on all of them. So we're going to need clock, because oscillator is not actually oscillator. Oscillator is clock. So I'm going to do instead clock init of 18,000,000,000. Okay. So now, when it comes time to actually run this, I'll be telling clock to please do stuff for me. Now I will need to supply reset in and ready in myself. Sync for the hypothetical future where we're testing in the presence of an 8080, then sync would come from the 8080. Meanwhile, I need to manipulate sync manually. Which means some of these tests are going to get kind of long. For the moment, it's not going to do anything, because for the moment, nothing is happening. So all we're doing is testing init. So what do we want to do here? On each rising edge of the oscillator, I want to step to the next state and do the things appropriate to that state. Or actually, I want to do things appropriate to the state I am in, okay, and then step to the next state. So we are going to need a static void I8224 osc rising. We're going to put this down above all of the test stuff. Which means that in linked, we need to do a bit of a hookup. So edge on rise, the edge is gen or osc. We're going to call this function. Come on, get it right, Greg. Like that. Okay, no fails yet because we're not doing anything. We're just establishing the edge. Means on power on self-test, I'm going to do one more thing. I'm going to assert gen arrow OSC arrow rise arrow len is greater than 0. And just to get something that will fail, actually, let's say assert it's equal to 0, that should fail. It does. So I'm going to say greater than 0. We're in a test scenario. The only thing that should be on that is us. Let's say equal to 1. So for power on self-test, we are going to assert that we are only listening to rising edges, because if we were listening to rising and falling edges, we would be substantially increasing our runtime for no benefit. Okay, now if I tweak this, yep, there it is, test condition failed. Expected value 1, observed value 0, well, we actually expect 0. We're going to repeat that inside BIST, so BIST doesn't assume that POST is testing this. Although I can do like I did before, and basically I'll make POST, and then I will maybe have it too big. I'll duplicate it, and then I'll trim POST back and expand BIST. So, test init, make sure we've got a rising edge. Our state is 1, so what I want to do is cycle the clock and assure that state has changed. So I'm going to start by assert EQ integer. This is an over test here. Bell's ringing. I was going to assert that my state was 1. For power on self-test, I'm not going to assert anything at all about being in a particular state. I'm going to demand, however, that the state changes. And either increments by 1 or goes from 9 to 0. It would be 9 to 1. I'm going to demand that it's changed. So int old state is int state equal to gen arrow state. And then we're going to say clock run, is that right? Clock run 1, yep. Assert NE integer, and the expected value is not state, and the observed value is gen arrow state. And I don't have an assert NE integer, so interesting. I did all of these except I didn't do NE. If I took the Q equals off of this, it'd be a lot simpler. There we go. Okay, so now we got to that stub. So I'm seeing a rising oscillator edge. And then I'm seeing assert not equal to state, and state is not changing because I'm not changing state yet. So now we can fix that. So I'm going to do a switch based on the current value of state and set it back to state plus 1. However, I don't want to do multiple writes. So int state equals gen arrow state. Okay, so there's that. I'm going to put in default assert. We need to do an assertion failure here. So I'm going to do a fail call. State %d is invalid, must be 1 less than or equal to state less than or equal to 9. Even though my code can't return, I still put a break. Okay, reformat, and there we are. So now we're stepping through 9 states. And we are passing that test that says state changed. But changing state is not the be-all and end-all. I really want to cycle through a bunch of things. Let's run it 8 more. I'm going to verify that if I run it 8 more times, it's going to come back with the same state for int I equals 1. So I'm going to clock 8 more times. I'm going to assert EQ integer. So a total of 9 calls to the clock should bring us back to the same state. In fact, I'm going to assert that before each call, like that. So we've run it once, and we're not equal to. We run it again, we're not equal to, blah, 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 and finally we get back to equal. So we observe value 10. Okay, well that's because here in case 9 I need to say state equals 1 to get us back to state 1. Now that is sufficient to catch the easy bugs, which is all I want to do in post. I'm not going to verify that over the course of 9 cycles we take on 9 discrete different values of state. That's overkill. In fact, checking to make sure that we are, if we were back in the same state, we'd be doing the same thing. So we really do need to have it that way. If we go from A to B and eventually we get back to A, okay, either we have gone through a cycle of 3 several times, or, but still, in order to get back to our initial state only after 9 and no sooner, that means we've got a period of 9 here. We don't have a period that's less than 9, so we're good. So now I need to start making some output signals. Okay, let's take the signals from the top of the block diagram. Phi 1. Phi 1 needs to rise inside phase 1, so gen phi 1, so edge high there, and in 3 we need to go edge low. And phi 2, we need to go high in 3. Most we're doing this edge low and then edge high. All of the consequences of edge low will complete, including anything tucked on any hypothetical singleton FIFO, before we start doing this. So edge high of phi 2, we go 1, 2, 3, 4, 5 down here. So during cycle 8, we go back low. During cycle 9, I am going to go edge low on ST, STB. And during case 1, we are going to go edge high on that. This is not exactly correct because the status strobe needs to be low when ready is set. So we're going to say if not, when reset is high, I need to keep this low. If not, gen arrow ready and reset. Oops. Reset is set, then we go edge low, else we go edge high. Now we also need some code in there as reset changes state to update STSTB. So getting STSTB set is going to be more complicated. And we do that by saying on edge rise of reset, it's on reset rise, and on edge on fall of reset is on reset fall. Now notice this is watching a signal that I'm setting and falling and clearing. So this means that when I change the value of reset, I don't have to have code that says I've changed reset, so I need to change this. Just wherever I set reset, it's also going to do this logic. So when reset goes high, I'm going to say gen arrow STSTB underscore edge low. And reset falls, I want to bring it high. And the difference is if we are in state 9, I don't want to do this. So if gen arrow state is equal to 9, then we still want to be low, else high. So if for some reason reset were to fall during state 9, we would fix it. Now, this is overkill because we are latching reset. Reset is the output of a latch that's going to trigger at a different time. It's going to trigger here in case 4. So case 4, what we're going to do is we're going to copy res in into reset while inverting it. So if actually, let's just say if res in is high, then reset goes low. Okay. So now we all know that state's not equal to 9, so we would actually be safe in just doing this, but I'm going to leave this here because reset does not change often, and having this here assures that we do the right thing if we change the logic ever in the future, or if there's a bug. So a bug that would change reset to do the wrong thing won't cause STSTB to also do the wrong thing. I like my failures to not cascade. Okay, so reset's set up. Now ready in and ready, we get the same thing. But when ready in is high, ready goes high. And if ready in is low on this edge, then ready goes low. Now, STSTB actually doesn't always go low in 9. So this logic is going to be wrong, so let's not do it. Okay, I'm going to go back on what I said. If we have a bug in reset, it's going to cascade on through it because the logic to set STSTB needs to live here. So if gen arrow sync is set, then we set this low. Now, I'm not going to explicitly change things whose state doesn't change. So yeah, if reset is high, that does that. Res in. So I could set this up as something to do with the edge here, but there's still the problem that I don't want reset or ready. So these guys, that means every time I reach phase 4, I'm doing all of that logic. It'd be nice if I could do it edge triggered based on res in and ready in, but I still would need to delay the change of reset and ready until phase 4, which still means in phase 4, I need to make a decision and toss it through edge. Okay, so I don't think I can eliminate that cost. Damn it. The other thing I can do is I have this paradigm where I'm saying if something is true, edge high, else the edge low. Let's augment edge a little bit. Edge has edge high and edge low, and how about we add something that sets an edge to a value. Edge 2. Okay, so if it changes, notify subscribers on the appropriate list. Okay, and the value there is a representation of a single bit in the destination system. Have I been consistent about that? I have. Bit value. Now we need to implement edge 2. And I think I can implement it more efficiently, runtime faster than doing a conditional call to edge high or edge low. So I'm going to pick up the body of edge low, and we are going to do this. Okay, so edge 2, given an edge and a bit. So if E value is not equal to V, do work when state changes. Busy, if V, we're going to do one run, else run the other one. So if V is high, we're rising, and value is V. So this is edge 2. So we deferred the entire decision based on V to here, so the rest of the code is completely common. Now, in theory, one could implement edge high and edge low as calls to edge 2, but that would mean that they would be, first of all, an extra function calls. You'd be calling a function that calls a function. Not bad if it's inlined, and it has this. However, GCC be one clever thing. I would not have done this in 1990, but GCC is so good at inlining and removing dead code that I'm going to do it. Edge high becomes edge 2 E1. So we're going to watch very carefully. The edge is sitting at 8 nanoseconds right now. I haven't compiled in a while, so I need to fix this stuff up. So on reset rise and on reset fall are now declared. So went from 8.0 to 8.6. How variable is it? Oh, 6.8. So edge time is highly variable, so we are probably not much worse. I would be willing to actually place a bet that what happens is it's going to inline edge 2. It's going to have a 0 here. It's going to say if 0, it's just going to get rid of that. And it may even inline subs run. I don't know. Well, it shouldn't inline subs run because it's a different compile module. Speaking of which, let's double check my flags. Okay, we are running OFast. Okay. Now I'm curious. Let me see here if I gdb bin live coding. There's edge high. So edge high is indeed inlining edge 2. There's subs run. So push, compare, move, jump equal to plus 67. Down here, up, there we go. So this is the escape because we're equal. These must be assertion failures. What if I comment out the asserts? Okay, there's edge low. Push, compare, move, jump down to plus 40. So this is the, well, this is the internals of that condition. So it says move, load effective address, move, call subs run, move, done. So indeed, it does eliminate the if, else, and subs run that don't exist. I wouldn't have done that in 1990 if I was worried about time. So for performance critical code, I would have inlined myself and optimized it. Meanwhile, compiler people saying, but we can inline that if you call these special things and do this special flag, and maybe it'll work, and maybe it won't work, and maybe I'll find a compiler bug. And yeah, but nowadays this just works. So I'm going to do it because it cleans up the code. So there's edge. So now we can come back here to the oscillator, and I can say edge 2 of not gen arrow reset. Okay. And edge 2 reset not gen arrow res in. And of course, I was doing a not of a pointer rather than value. Danger, danger. Because not pointer is of the right type. So it wouldn't have caught that. So there's our logic. And I'm going to do the same thing. Yeah. No, this says if gen sync is not set, we don't even bother doing the call. That saves time. So we do the if here before the call rather than doing the call, doing a bunch of overhead, and doing an if in the middle of it. So what is this set for us? We now set phi1 and phi2. We have set STSTB based on sync. We have set reset. We have set ready. So now we need to test it. We are in reset right now. Reset is going to be holding STSTB low. So I am going to assert that reset is, I'm going to assert that that's still true. So after those 9 cycles with, let's assert our initial condition. I think it's more clear if I say 0 is equal to the value. And initial condition is reset in is low. I'm also going to assert that ready in is low. I'm going to assert my initial value of my reset and ready outputs are low. Oh, ready is 1. There we go. So independent of how we're coming in, if we get to this test, I want this test to start with us in reset configuration where reset is active. Reset in is low, ready in is high, and so on. Ready in is low. This configuration here. We're going to do that for 9 cycles. These first 9 cycles, we're testing that the state does the right stuff. And I also want to assert that status strobe is starting out at 0 and it's going to stay there. So we're going to do the whole set of things here. Nothing should change during these 9 cycles because we are sitting there humming in reset. Let's do it for another 27 cycles. So 3 more T states. We don't want to use clock run 1. What do we want to do? I want to do clock run until. The best way to do this, and if I don't want I-8224 to know that tau increments by 2 per clock, then I need to do a clock run until clock future tau of some number of microseconds. Well, the nanoseconds is 1500 nanoseconds. And then I'm going to fprintf standard error at end of post tau equals %LLD. So I end up with tau at 295 at the end here. We're going to go to the top. We're going to say at top of post. So it went from 223 to 295. So that tells me there. So I incremented tau by 72 during post. We're doing it twice because we're doing it once at the start, and then we're doing it again when we run the benchmarks. So we run our post and our BIST, and then when we run benchmarks, that's a separate execution. It forces post first. So we ran a total of 72 because we clocked here by another 1500 nanoseconds. At that point, everything is still there. Now, we're at the beginning of a T-state. We don't sample until the middle, but what I'm going to do now is I'm going to raise edge high gen RDY in. So I'm going to deassert, reset in. I'm going to deassert ready in, and res in. And we're going to run for another 2 microseconds. So 4 more T-states with reset released, but ready still active. And we get a failure here because res in changed. Well, I just changed it. And actually, let's edge high res in. We just asserted everything else. We don't need to assert again. So this says reset value is now 0. Okay. Now, what would be cool would be if we could reach in and say, how long ago did reset actually change? Well, wait a minute. Edge.h has this nifty little thing called when. And this will tell us the last time it was, the last time the value was asserted, even if it didn't change. What I want is to know the instant that it changed. So what I'm going to do is I'm going to attach an observer to reset for testing that will tell me when reset changes. So it will look a lot like these. It's specifically for this test. This is separate from the runtime. The normal runtime will have these that needs to do. But after that runs, I'm going to have a second subscriber here for power on self-test. And what they are going to do is I want to kind of have some information about when things rose and fell. Well, one of the things we do is we compare outputs. During post, I need to be silent, so I need to be able to assert. We'll figure out what I'm asserting later. During built-in self-test, I can print and have it do something reasonable. I'm wondering if maybe, yeah, for post, I will just assert that it happens. The built-in self-test will do things more strictly. So these are in, test becomes in bist. And we'll worry about that later. So all we are saying is that in here, when I change res in, I want it to be recognized sometime in the next 500 nanoseconds. And not go away that far. Okay, we're going to get warnings about this guy not being used. That's all right. Okay, so we're verifying that it's changing. To do in bist, connect monitors to signals that print, including elapsed sim time in test, sig name, new and which edge. So that's res in. Next thing we want to do is ready in. So we're going to bring ready in high. Oh, I did that too many places. Ready in has gone high, and we're going to assert that ready is now high. And that's passing. So reset and ready are being done at the right time. I also want to be capturing the fact, that phi 1 and phi 2 are doing the right things. So altering this time, phi 1 and phi 2 should be wiggling such that each one of them goes high, goes high, low, and it can get the right number of things. So I need an incrementer, and I'm going to static void test incr int star CTR. Generic utility function. I use that kind of thing all the time. So I want to count rising and falling. Actually, I want to count rising. Yeah, count rising and falling edges on each of the phis. Why am I doing that? I'm not going to be resetting this counter all over the place. I'm just going to set it. And when we're all done, we're going to check the number of times that it did it. Now, I could put in checks that phi 1 and phi 2 are never high at the same time. There are all sorts of timing checks that we could do. Now, how many times should I have seen the clocks rise and fall? So this is one t-state here, 3 more t-states here. That's 4, 5, 6, 7, 8, 9, 10, 11, 12. So I should have seen 12 edges on each clock. That initializer should be there. And that passes. So what do we have in our post so far? We know that we are in a 9-phase clock. We know that reset and ready are being latched inside at least, if the input's there at the beginning of the t-state, then at some point during the t-state they're being latched. Good. And we know at the end we got the right number of rising and falling edges on phi. I haven't done anything with STSTP yet, but I'm going to take a break at this point and get some dinner. And when I come back, we will finish up the power on self-test for the 8224 and expand it into a built-in self-test and maybe work on bench. This is kind of a significant module, so it's not surprising it's taking a little extra time. So I will see you in the next session.